Hi everyone. So the goal of this video is for you to explain and calculate work and power. So what is work? In our everyday lives, work can mean a specific task or assignment, or activity that a person does to earn a livelihood. Now in physics, we use a much more specific definition, and it might not be so intuitive. So let me make sure that I go over that. So what is work in physics? In physics, work is force performed over some distance. So if you're applying a force and you're able to make something move over some distance, then you have done work. So in these two pictures here, we have a person pushing a box across a floor, and you can see they're pushing with a force and they go some distance. Or we can have a power lifter that maybe lifts a large mass a certain distance above their head. You can see if they do 200 newtons of force and they make it travel 2 meters, then they have done some work. So if I'm ever going to ask you for a calculation on work, work is force times displacement. Or another way that you might see that written is W equals FD. Right? So every time you see those two letters like F and D next to each other, that just means that you're multiplying those two numbers together. And the units of work are joules, which we've talked about before. If you watch the other videos, or maybe even in class you've heard this term, joules. That is our unit for energy as well. So work and energy have the same units. So let's talk about how those two things are related, work and energy. So doing work leads to a change in energy. So to give you a specific example, let's say a person is pushing a wooden box, so the wooden box is stationary on the floor, and then a person comes along and they push that box with a force, and the box moves. In that case, the box has gained kinetic energy. At first, its kinetic energy was zero, right? Kinetic energy is related to movement, and if it's not moving, then it has no kinetic energy. But if someone comes along and makes the box move, now the box has kinetic energy, and it gained kinetic energy. To gain that kinetic energy, something or someone must have done some work. In this case, the person. So the person did some work to make the box move. And so, assuming that there's no friction and there's no loss of energy, then the work done by that person is going to be equal to the energy gained by the box. So work and energy are very much related. And so the equation actually is pretty simple right here. So work is equal to the change in energy. This is called the work-energy theorem. So work is equal to any change in energy. All right, so what is power? Power is work done per second, or a change in energy per second. If you looked at that in terms of an equation, you take your work and you just divide it by time. Or you take your change in energy and you divide it by time. And our units of power are watts. Now, watts might be a term that you've heard before if you've ever seen, I don't know, a light bulb. So you might hear of 40-watt light bulbs or a 60-watt light bulb. Right? That's how much power the light bulb is using. All right, and so you'll see many different light bulbs that have different watts and things like that. But that's just how much power it uses. Speaking of power, I think this is a common question that I usually get almost every year when I teach this class, so I'll just address it now. This idea of horsepower. Horsepower is actually a measurement of power, and 1 horsepower is equal to 735.5 watts. Now, where this number actually came from, it's a long story. It actually comes down to the person who came up with the idea and the measurement of power, who was named James Watt. And I'll say it again, as I've said it before in class, if you discover something or if you come up with a concept, sometimes you can kind of name the units after yourself. So there's a lot of things in physics where the units we have are named after a person, like newtons are named after Isaac Newton, joules are named after James Joule, watts are named after James Watts, volts comes from volta. There's a lot of different of these terms that are just come from the scientists who came up with a major concept. Anyways, So let's just go over an example of work, and let's go over an example of power. So let's imagine that there's a bobsled team and they have to push their sled. Now their sled has a certain mass, it's 350 kilograms, and they're going to push it with a combined force of 1,200 newtons. And they're going to push with that much force for 25 meters. So if you've never seen bobsledding or if you're not too familiar, basically 4 people will push this sled and they have a certain distance to kind of push it, give it some kinetic energy, get it some speed, and then they all kind of jump in and then they go down this course for about a minute. So after about 6 seconds, they all jump in the bobsled and they head down the hill. So my question is, how much work did they do and how much power did they produce? So let's look at some of the numbers that we were given and then we'll try to figure out our unknowns. So some numbers that we were given. Force is equal to 1,200 newtons. Distance or displacement is 25 meters. Time is 6 seconds. And the mass is 350 kilograms. All right, so let's think about what equations do we need to find work and to find power. So one equation that we were just introduced to is work is force times distance. So I have force and I have distance, so I can figure out work pretty easily just multiplying those two numbers. So I'm going to multiply 1,200 times 25, and I get 30,000. And again, the units are joules, so I'd say my work is equal to 30,000 joules. Or I could also say they did 30,000 joules of work. Now for power, I also have an equation for power. Power is work divided by time. So now that I know work and I know time, I can easily figure out power. So in this case, power is going to be 30,000 divided by 6. And I would say that the power is 5,000 watts. Or another way to say that is they produced 5,000 watts of power. So those are just a couple of examples on calculating work and calculating power. All right, so I hope this was useful. There probably will be some practice questions for you to try to answer when it comes to work and power. So good luck with that.